All right. Hi, everyone. Hello again to folks who came to the original workshop, and welcome to anyone that's new. I thought I would start by, so I'm going to show my slides through the Chrome tab here because I'm going to need to be flipping back and forth between slides and an RStudio or terminal window, and I think this will make it a little bit easier. So the idea behind today's workshop is to try and address some more advanced computing topics involved in working with the computational resources that we have available um, to CAsToR members, um, which which the first workshop kind of introduced, and I'll say a little bit more about that just kind of so that everyone's on the same page. So very briefly, a little bit about myself. I'm Michael, obviously. I think I'm a research specialist now. Before that, I was a postdoc, and before that, I was a PhD student at U of M. A lot of my focus has been on mathematical and computational modeling. My research focus, that is, but alongside that, I am really interested in computational methods and working with higher performance systems, and I like to build computers, so that's how we ended up with the T-core systems. So I think I didn't do this the first time, but I'd kind of like to this time because it'll help me kind of get a sense for where everyone's at. If you don't mind kind of going around and giving a brief introduction for the participants here and say, I guess, a little bit about what you work on, whether at U of M or Georgetown, and maybe a little bit about what your computational experience is, how comfortable you are with computers, what sorts of platforms you're used to working with, things like that. So I guess we'll just kind of go down the Zoom participant list.
Well, it seems I'm the first one. Hi, I'm Eugene. Hi, Michael. This is Eugene from Georgetown University. And I'm a statistician in Georgetown University. And I had some experience with RStudio server. I think I've installed like almost 10 years ago.
Oh, nice.
I installed RStudio on a Amazon, like what is it? Cloud computing.
Okay, yeah.
Amazon used to, in the first, like Amazon used to promote their cloud computing like almost 10 years ago. And they have some product called EC2. I'm not sure if you know that. Like elastic computing.
They still have a version of that on their
They used to have a free
platform.
tier. I tried their free tier version.
Oh, that's neat.
Right, I think that's
Nice
all.
to meet you.
Oh, nice meeting you.
And are you using mainly Windows or Mac or Linux? What platform?
I happen to have 3 computers in different systems.
Oh.
In 3 different systems.
Means that you are familiar with all.
I have a mixed family like that too.
Okay.
Let's see. On my list, I have Luz next.
Okay. Hi, I'm Luz. I'm from Georgetown. I'm working with the Georgetown team. So familiar statistical programs or just, so I use Mac and Windows. So I use those. Statistical programming, I was mainly trained in Stata, but now I'm trying to move to R.
Neat.
Yeah.
And let's see, next is Irina.
Hello, I'm Irina. I'm from U of M and I'm a statistician, and I mostly use Windows. In terms of the languages, I used RStudio before, but R is not my primary language, but I from time to time program in it, and I'm more or less familiar with basic things. I'd like to learn more about parallel computing and how to be efficient with computations. Currently, I'm trying to run M+ on the server and actively learning M+.
Yeah, this has been interesting for me because M Plus is not a platform I'm familiar with at all, so I don't have a sense for how it uses and allocates resources particularly. So, um,
It's interesting. I found that it's actually, I can specify a number of processors or cores, so they call them processors to kind of
mhm.
to encourage parallel computing, but there are some other issues I'm still in the process of figuring them out.
Right. Neat. Um, let's see. Next on my list, I have Jihoon.
Hi everyone, I'm Jihyun. I'm a research faculty in the UM, and I'm also co-leading the DAD core in the T-Course Center. And I have been, I'm a cancer modeler using the mathematical and statistical tools. And my main language is like R, or I used to use the Fortran before, but not much these days. But so I would say mostly I use R these days. And I'm mainly using Mac and also Linux for my work. And what else? I think that's it. And I have been using the T-Course servers, so and also doing some parallel computing there. But it would be nice to hear more from Michael if there is any better way to handle parallel computing.
I'm not. I've seen your parallel code, and it's cleverer than mine. So I'm not sure how much I have to add there, but we'll see. Hopefully, this is interesting still. Um, let's see, Marie. I think you're next.
Hi, I'm on the Georgetown team, and I use Windows and am most familiar with SAS, but hoping to learn R as well. And sorry, there's some construction going on here, so I hope you can hear me okay. I'll just stay on mute for the most part.
Oh, no worries. I can definitely hear a jackhammer though, so
Yep.
that's exciting.
Hi, just to add something. So Mari just started with the Georgetown team beginning of this
neat.
month, and she is gonna help us with part of the work that Chris was doing. So you're gonna see her more in the emails and everything.
I see. Great.
Welcome then.
Yeah.
Let's see. Who do we have next? Evelyn.
Yes, hi, I'm Evelyn from U of M. I work in the DAD part, the CAsToR, and I use Windows, and my main language is Stata also, but I've been using R since I started working at U of M, and Julian has helped me a lot.
And Evelyn, you haven't really done any parallel computing yet, right?
No, I haven't.
So this would be a nice introduction.
Yeah.
Great. Let's see. Buki. I think.
Yeah. Hi, everyone. So my name is Buki Usidame. I'm a postdoc research fellow at the University of Michigan. I work only, not mostly, on Windows, and I use data almost all the time. I've tried my hands on R, and yeah, that's where I'll say. So I'm just here to kind of stalk and see how it works.
So that's always good. R is an adaptation coming from things like SAS and Stata, I think.
Yeah.
Let's see. Tui?
So, hi everyone, I'm Thuy. I'm a postdoc from the U of M. So I am familiar with C, MATLAB, and R. So I have some experience in parallel computing in R as well. Yeah. So most of the time I'm working with Windows, but recently I moved to Mac.
Neat.
Yeah, that's it.
Were you in the first workshop, or this is your first?
Yeah, I did. Yeah.
Oh, okay. So then, could you like connect to server?
Yeah, I did try to run some piece of code on the server as well.
Okay.
Neat. Let's see, next we have Steve.
Hi, everyone. My name's Steve. I am a postdoc at U of M working on the CAsToR projects. I come from more of the world of social science, and I was a faculty in the UK and Canada for the last 10 or so years. So it's been a little bit of a learning curve for me. I'm a Stata user primarily. I'm trying to learn R, but it's taking me a little bit longer than I anticipated. And I use primarily Mac right now, but I also use Windows when it works properly.
Maybe the same question. Were you in the first workshop, Steve?
I was, yes.
Ah, okay. So you could then, okay.
Yeah, and I was able to connect to the server without a problem, but I haven't tried it on the Mac ecosystem, so we shall see.
All right. Well, that'll be exciting. And next, Jasmine.
Hello, everyone. Hello.
Hi.
Hi, everyone. I'm Jasmine from Georgetown University. I'm a biostatistician, and my major is statistics. I use Windows systems. I usually use R and SAS in my daily work to do data analysis. Nice to meet you. I'd like to learn the computing skills in R.
Neat. Nice to meet you too. All right, so we have a wide range of experience across different domains, so this will be interesting. Computationally, I am primarily a Python programmer, so R is a language that I use grudgingly. It's good at some things, but frustrating for others. But I'm going to kind of focus on parallel computing in R for this workshop because I think it's kind of a good sort of common language for basically everyone here, and it showcases some of the themes that I wanted to emphasize. Like I said, I have a mixed computing family, so I work on Windows, Mac, and Linux. So hopefully I'll have some sense for how connection and stuff works coming from different platforms. Luckily, one of the nice things about connecting to the TCore servers is that it's basically platform independent. It should not matter which system, which operating system you're trying to connect from. Obviously, if you connect by SSH, that's completely independent of your operating system. Every modern operating system has an SSH client built in. And if you're connecting to the RStudio server, that actually uses a browser-based connection method that just requires that you have a web browser. And if you are, one of the reasons that for our Georgetown participants, the reason that I asked you to download and use the Cisco VPN client is because to connect to the RStudio server via browser, you have to be connected to the U of M VPN because it requires that you either be on a U of M network or the VPN equivalent to actually connect there. SSH doesn't have that requirement because of the security inherent with that protocol, but RStudio server is on a port that I've only had ITS open for university networks for safety purposes. So thank you for letting me do the little introduction round. Today, what I wanted to go through was a few topics. So I'll start with a quick review on connecting to the CAsToR servers or the TCore servers. I'm never actually sure what to call them that way. I'll have a little section of miscellaneous unsolicited advice about programming and working with sort of writing your own code and debugging and things like that, primarily focused for folks who have not thus far done a lot of computational work and tend to come from platforms like Stata and SAS and things like that. I'll talk a little bit about how to quantify and think about program performance and bottlenecks, because that's a lot of what underlies the rationale for parallelization itself, trying to get around certain types of bottlenecks, and sometimes in so doing, creating new ones for yourself. So there's a couple of moving pieces here. Just as a reminder, the CAsToR server resources right now comprise three systems. They are T-Cores 1, T-Cores 2, and T-Cores 3. Of these, the ones that most people will be working with are T-Cores 1 and T-Cores 3. T-Cores 2 is kind of a strange system. So T-Cores 1 and 3 are designed to be a large core count system. They have 64 and 128 cores respectively, so they're intended to handle larger numbers of users and more parallelized workloads, where T-Cores 2 has a small number of really fast cores, and so it can't support the same kind of simultaneous user load that the other computers can, which is why it is more reserved for as needed work primarily by the PAs. But I think the idea is that folks could potentially request it if they have applications that would work well on that system. Generally speaking, as I kind of alluded, there are two ways of accessing the CAsToR systems. One is through SSH, or secure shell hosting, which is basically a remote terminal connection. So this is a command line connection, basically. And like I said, it does not require the U of M VPN to work. The other method of accessing the CAsToR systems is via RStudio server, which uses a client-server interface. There's basically a server instance running on each of the CAsToR systems, and then you can connect to each of them individually using a browser client, which I'll demonstrate a little bit through this session. And if you watch the first workshop, I spent more time going through how to actually log in and connect. So I think I'm not going to spend an enormous amount of time with that here. I have I've replicated instructions from the original workshop for how to connect to the CAsToR systems via SSH and using the RStudio client. If you're connecting via SSH, this is going to depend on what operating system you're coming from. If you're on a Linux or Mac system, then you can SSH direct. You know what? No, this isn't true anymore. If you're coming from any of the systems, you should be able to SSH through the terminal, because even Windows systems now have included a real OpenSSH client as a command line utility. That said, if you're coming from Windows, the default Windows terminal is the command prompt, which is that ugly little black and white window, which is a terrible, terrible terminal interface. So if you are coming from a Windows system, I would strongly recommend that you use PowerShell instead, which is an alternate terminal interface that's built into Windows operating systems, and it gives you a more Unix-like syntax for things. So a Unix-like syntax will look a little bit more like a Mac or a Linux operating system at a command line level. I just find that it's easier to work with. And commands that you put in through PowerShell will tend to look a little bit more like commands that are going into Linux or Mac machines through the terminal. That being said, also, one thing to note about if you're coming from a Mac is that secretly every Mac is a Unix system, essentially. It's running a fork of the Unix operating system under the hood. So underneath all of that fancy Mac OS GUI, there is an underlying operating system kernel that looks a lot like a Linux system or an old Unix system, which means that the Mac terminal gives you access to basically all of the commands that you'd be used to if you're coming from a Linux system, which can be really helpful in kind of working between the two. Things will look more familiar. So I've given here the addresses for each of the CAsToR systems. I think we'll be focusing on T-Cores 1. I should have made everyone an account on T-Cores 1 right now. So if you were not in the first session or the first workshop, then I've made you an account on T-Cores 1 where your username is the unique name that you were given when you were made a U of M affiliate. And if you have not accessed these systems before, your password should be change me in all lowercase. And I would recommend looking at the original workshop slides for how to then change your password, because please don't keep that password. To connect via RStudio server, which is more of what we'll be doing this time, this is, like I said, this is a client-server system where you connect via a browser client, which is really quite cool and has a lot of neat features. You need the U of M VPN to be active, or you need to be connected to the U of M VPN. And if you have not already done that, there is a link to the U of M IT guide for how to do that. Hopefully everyone has been able to, and please let me know if you've had trouble with that. When you go to access one of the TCore systems via the RStudio client, I guess I should call it, what you're going to do is enter the address of the system :8787 in a browser. So I'm using Chrome, which I know works. Firefox, I'm pretty sure works. I'm pretty sure any modern browser should support this. So if I was connecting to UMTcores 1, this is what I would put in the little URL bar up here. And that should take you to a login screen that looks like this, where you can log into that system using your system username and your password. And then it should take you to a screen that looks a little bit like, let me swap tabs, a little bit like this. So what you'll see when you log in via the browser client is a fully rendered RStudio instance. This should look almost exactly like the RStudio desktop interface. I think there are a few differences. One of the cool things that you can do with this, so for one, because this basically looks like RStudio desktop, it means that if you're used to working in RStudio, this should not be any kind of big jump. It does include some nice extra features like the ability to, it has an intrinsic file browser of the system that it's running on. So this is a file browser of the actual TCore server, which means that you can upload files to transfer data to the server if you don't want to use SSH and SFTP and things like that. You can also export or download files from the server, so that's how you can move scripts to and from that system or data to and from that system. It also has access to a terminal interface to the system, which is what I have open down here. So this is just a Linux terminal instance, basically, and I was using it earlier to create user accounts for some of the new members. There is also a new feature which I haven't had a lot of time to test out, but which I think is potentially quite powerful, which is this Jobs tab in the console window down here, where you can submit scripts as jobs on the server. So this is a way of doing what's called batch processing, which I'll talk a little bit about later, and it enables you to kind of run and manage scripts that might take a bit to execute. And this is important because one of the limitations of RStudio's client-server interface is that you can only have one connection to a server per user. So I couldn't open another browser window and put in the login information and have two separate instances like you can do with SSH connections. It'll only allow one per user. So my impression is that this jobs system is a way of kind of getting around that to allow you to run multiple scripts per user instance. So that's potentially quite powerful. Anyway, again, I think most people have seen some amount of this from the first workshop. So I'm not going to spend a lot of time there. If you have questions about that sort of stuff, please do feel free to ask, and I can try to address that.
Michael,
Otherwise,
I have one question here. So in the terminal you just showed, the terminal looks like it's like a regular terminal window.
Yes.
But this comes through the RStudio. So does this mean that you can run R script with some command line here, but only R script would be?
No. So this terminal is a fully featured Linux terminal. Like this is, you can do anything that you could do in a regular terminal in this terminal window. Like I could run Python jobs through here.
Oh, that's great. Okay.
So here I've just started a Python 2.7 interpreter. So this particular terminal instance in RStudio server is actually a real full system terminal. The console is that's the specific R prompt. Like this is the equivalent of starting an R instance normally. So here, having started an R instance, this is equivalent to the console that comes with RStudio. But otherwise,
it should be like a regular terminal.
yes, as far as I can tell, it's fully feature equivalent to the system terminal. Like I could write and run shell scripts through here if I really wanted to.
This is good to know. So then maybe Irina, she can try also run her SAS code here, right?
Theoretically, yes, because you should have access to any program which is installed on the system.
Okay.
Yes, thank you. It's interesting. I will try. I was using PowerShell last week to submit it, but I'd like to compare. And if you can remind us how we can get to this RStudio, it would be very helpful. Maybe you will do it in a minute.
So, so the way that you connect there is actually just to so the address I have here does the URL bar for this window show up in the screen share? I can't tell. Preview is extremely small.
Don't think so.
Okay, let me try to switch to the actual Chrome window I have for this. Okay, so here,
I see.
Does that show the entire Chrome
Yes,
interface?
yes.
Cool.
Yes.
So what I've done here is I've put in the system address and then :8787. So, and then if you tell the browser to go to that site, it will take you to the RStudio client interface.
Thank you so much.
And what it should prompt you to do is sign in, and the sign in that you use is just the same login that you would use to connect to the system via SSH from whatever terminal you're normally using.
Thank you, it's clear.
Perfect. All right, so that is a little bit about the RStudio system, and I'll demonstrate working back and forth between the actual R console and scripting interface in RStudio and the terminal, because I find that helpful for monitoring system resource usage while I'm running jobs on one of the systems. So I'm going to move on to a little bit of unsolicited advice first, because when we're doing a lot of our parallel computing, we tend to have to write the code to do that ourselves. Some platforms come with packages that have parallel stuff built in, like it sounds like M+ has nice parallel computing infrastructure built in. SAS to a certain extent does too. Stata sort of does. You have to pay for it, which I think is annoying. But broadly speaking, we do tend to have to write a lot of our own code for this sort of thing. So when I think about writing code, I think it's helpful to have some rules of thumb in mind in order to make sure that your code is manageable and readable and kind of reliable. So I would argue that well-written code should be the following. It should be explicit, which means that your code should make your program logic as clear as possible. When you name variables and functions, you should give them descriptive names that tell you something about what they do and what type of variable they represent or produce. And largely this means to me that your program code should not try to bundle too much stuff in any given line. I tend to find it preferable to break things up so that you know what steps your program is taking when it executes. This also helps your code be consistent, which means that it behaves in a predictable way based on the input you give it. What you don't want is code that you don't know what it will do when you give it some input. And I think this is something which can be tricky when you're running a statistical analysis, where a lot of times the functions for statistical analysis are not very explicit because they bundle an enormous amount of underlying code into what's effectively a black box. And so it's often hard to tell what's actually going to come out of that box when it's finished running. And I think it's helpful when you're writing and running code for statistical analysis, but for anything, to have a sense for what the thing is doing under the hood as much as possible, which means reading the documentation for your functions, understanding the statistical methodology that you're using in order to be able to have some sense of if something goes wrong, or if I'm getting a result that I don't expect, what possible step along the way could that be happening at? Good code should also be safe in that you don't generally want your code to have access to too many system variables or variables in general. A lot of times I think when we're writing code, it's tempting to write code that has access to global or environment variables because it's easy to access them. But what that tends to mean is that it's also very easy to modify those variables within your code, and anything which is easy to modify is also very easy to accidentally modify. So if I have a global variable which is an important parameter for my model or my analysis, and at some point along the line I change the value of that in my code, but I don't remember that I've done that, that can make it very easy to mess up subsequent analysis that I run that relies on the value of that global variable. So generally speaking, when I write a program, I like to try to make sure that functions and methods do not have access to much more than they absolutely need. That when they're working with information, that the data they have access to is only that which is passed into them explicitly. And that helps me control what is actually getting worked on in the code and what actually gets changed. And at a larger perspective, you don't want code that can access too much, because this can create security holes that malicious actors can exploit. So generally speaking, you want to avoid things like evaluate statements that can take arbitrary strings and run them as though they were actual lines of code. You don't generally want to have things which have too much access to your system variables or too much access to global variables and things like that. It's also good to make your code well documented, to use comments liberally. This is an area that I think I'm not even very good. I don't think anybody documents their code as much as they probably should, but it's always just kind of a thing to have in mind, that the easier it is for you to tell what your code does if you come back to it 3 months later, or if you hand it off, generally speaking, the better. But obviously, a lot of these things run in conflict with the fact that when we're writing code for an analysis or a model, we're doing it under a time crunch, and sometimes we just have to fix problems and implement things. So there's not always time to do these things. But I think it's helpful to have guidelines for what you're doing in the back of your mind, so that you don't end up just writing spaghetti that that you can't interpret 3 months later. And inevitably, when you're working with a new language, or when you're working with a familiar language, stuff is going to break, and you're going to get errors, and every time you write something, it's going to give you errors, and stuff's going to break. So if, particularly for those of you who have not spent a lot of time working with computing platforms, or working with programming languages as opposed to sort of specific purpose applications, I think I have found that for folks coming from that background, errors tend to be alarming. And I think what I would encourage you to do is to treat errors as helpful things. When your program throws an error, this is good. In some ways, what you want is, if your program does something wrong, you 100% want it to throw an error and break, and you absolutely do not want it to keep running, which some things will do. And that's sort of one of the most dangerous failure modes of code, is for it to keep going without telling you that something went wrong. So when you get an error message, it's generally best to read it carefully, because the error message will often give you a hint for what went wrong and where it went wrong. And it means that it gives you a link to something that you can Google if you want. So when Python throws errors, it'll usually throw errors of specific kinds, and that means that I can Google that type of error and try to get some sense for what's causing the underlying problem. Usually system error messages of various kinds will point to lines in your code that threw the error. That said, R does not have the best error system that I've ever seen. If you're running stuff through an interactive prompt like through RStudio, it will usually tell you where something goes wrong. But if you're running something using the R script command at the terminal level, it does not usually tell you where stuff breaks. So this means that if you want to, if you need to go and dig that up, there's a little bit more work involved. Usually one of the first things I'll do when I get an error is to double check the syntax of the line at that error, because sometimes it's just a matter of leaving off a parenthesis or misspelling something or forgetting an argument that I need to pass to a function. So that tends to be kind of my very first heuristic for how do I check what's gone wrong. After that, then what I usually want to try and do is trace down, did that problem happen from as a direct consequence of the line that the error message is pointing to, or is it something upstream? Did it happen because this line is getting fed some garbage that got produced earlier? And so what I'll try to do is I'll trace back in my code which things feed inputs into the line that threw the error, and do any of them, A, are there syntax errors in any of those lines? B, does it look like any of them could be producing output which is unsafe? And in order to do this, it's really important, I think, when you're writing your code and designing it, to just kind of pepper the thing with print statements that display intermediate results. So if you have a calculation which does an intermediate part of your analysis, like generates a random number or reprocesses some data to round something or square it or anything like that, I think it's helpful to make your program print that out to the console, because that means that you have kind of a journal that you can walk back through to figure out, well, this line crashed, and I can see through all of these print statements that this other line way back up in my code that feeds it is producing a number which is ridiculous, and so I need to figure out what happened there. So again, this is something that I'm not going to spend an enormous amount more time on, but I think these sorts of things can be helpful in terms of tracing down where your inevitable bugs are coming from and how to resolve them. It can also be helpful to monitor your program execution to see what they're doing, how long they've been running, how many resources they're using on the system, because some of this can tell you if something could be going wrong also. So one of the quickest ways to just kind of get a check on what the system's doing is the top command on a Linux operating system. I think you can do this on Macs too. So this is a basic system monitor, and if I swap back over to RStudio here, and I go to my terminal, if I enter the top command, it's going to give me a basic system monitor for T-Cores 1. And here I can see that, so I have kind of a summary of what the system is doing. It shows that 4.3% of CPUs are being used by user stuff, and a decent amount of total memory. I think that's what might be like 52 gigs are being used, and so on. I can also see, well, I think in my case, because I've been an administrative user, I can see who is running what. So I can see that Arena has 5 processes running and Giala has 1. And I can see how many resources they're using. So this also gives me a sense of, so Arena's processes are using about 11 gigs of memory per. And each one of them is using a core on the system. So, and I can also see roughly how long they've been running. I think this is in minutes. I'd have to check the exact time thing. But this can be helpful to determine, has something been running for longer than you expect? Is it using more resources than you expect? One sign of a program which might be doing something unfortunate is if, when you're watching the resource monitor, if the memory usage increases consistently, this can mean that your program is doing calculations which cause it to continue to store more and more stuff on the system, which often means it hasn't been able to resolve a particular calculation and therefore clean up memory that it's using somewhere else. So these metrics can be pretty helpful that way. Another thing you can do if you're more interested in just seeing what you specifically are doing are, let me swap back. or is the PS command. So this displays processes associated with specific users. The default, if you're not an administrative user, I think, is to show processes associated with you. You can also use PS -aux, which is giving the PS command some additional arguments to enable it to show more elaborate input for all users that you have access to see. So again, if I swap back to the terminal here, and I say PS-aux, I can see that that I get this big pile of output that tells me every process running on the system and who's running it and how much stuff it's using. This is a little bit, possibly a little bit more than a given person might want. Certainly in my case, because I'm an administrative user, so it lets me see everything. So if I want more specific output, I could do something like I could for those who saw the previous workshop, the grep command searches for a given text string within a text buffer. So that could be a file. Grep is actually really cool because you can use grep to search like data files if you're curious whether a particular user or participant exists in a data file you've uploaded. You can actually grep that data file. Alternatively, what I've done here is I've piped the output of PS-aux into grep, so it's searching this whole mess for anything which matches my username. So what this is telling me now is these are all the processes that I specifically have open, and here is their information. So here's their process ID, their memory usage. It's not telling me the column headers, which is a tiny bit irritating. But this can be helpful for getting a quick view of what you actually have running. The process ID is helpful because if you suspect that you have a runaway process or one which is hanging or stuck, you can use the kill command to stop a specific process. So if you use kill and then put in the process ID of your specific process, that should tell the system to stop that particular process. So that's a little bit about system monitoring. And this I find extremely helpful, particularly in monitoring parallel jobs, because you often want to know how much stuff are they using on the system, and is that expected or is that abnormal? So let me move on then to a little bit about program performance and bottlenecks. So I'm going to start here by a little bit of an introduction to what's actually happening within your computer, or what your computer is made of, what any computer really is made of. Inside pretty much every computer that exists, there's your processor, which is what's doing the grunt of your calculation work. But in order to do that, your processor has to talk to a few things. One of them is your memory, or your RAM. This is like human short-term memory. So this is where the processor sends data that it's actively working on. The other storage system on your computer is, well, it's long-term storage. This is your hard drive, your solid-state drive, things like that. And that's where you tend to write or read data that you don't need to work on immediately. So a common pipeline is if you access a data file or a data set that's stored on your hard drive, what your processor is going to do is read that data file into its memory, into its RAM. And that way it can work on that data file a lot faster than if it was directly reading from storage. And the main difference here is that your long-term storage has a lot of capacity. It can hold way more information than your memory can on a system. But it is orders of magnitude slower to read or write to that thing. So what your system wants to do is put anything which it's actively working on in memory. And if you're familiar with a little bit more about system architecture, there's actually a lower level layer still. Your CPU has what's called a cache. And the cache is basically a storage partition on the processor itself, or it's storage hardware on the processor itself, where the processor keeps things which it's working on even more immediately than things in RAM. And that cache is even faster to access than the memory itself. So what your system's actually doing is it's writing stuff from memory to cache and then working on that, putting it back in cache and then sending it back to memory. So your system intrinsically is trying to load data that it needs to run into kind of the fastest storage area it has that can hold that data. And then, of course, once your CPU is done working on stuff, it'll pass things either through the graphics processor or directly out to your display, which shows you what you've done. So when you write a program, that program is first stored on your hard drive, then your CPU loads the program into memory. It determines whether it needs to load any other stuff into memory to run, and then it executes a series of calculations which comprise that program and spits the result out to your display. This particular architecture of computers means that there's a number of places where programs can get bottlenecked, where if you're relying heavily on one part or another of this whole system, you can run into slowdowns. So program bottlenecks tend to happen in one of four places. You can have CPU-bound programs, which are things that take a large number of calculations in order to work. There are memory-bound operations where the thing that you're working on takes up a lot of space in memory. This is often the case for working on really big data sets. Like if you have a data set which has millions of rows and has millions of variables in it, this is going to take up a ton of space in memory, even though any given entry in that data doesn't take up a huge amount of space. And so in order to store that thing, your system, well, for one, your system might not actually have room in its memory to store that entire data set at once. And even if it does, it may not have room to store copies of it which it needs to work on. And modern operating systems have ways of getting around this. One is that if you're working on a Linux or a Mac operating system, you might see a thing in the system monitor called swap. And what swap basically is extra space that the system is allocated on the hard drive, so on your long-term storage, to act like memory, to act like RAM. So it's sort of your overflow. If your system realizes that it's trying to load too much stuff into RAM, it'll shunt some of that stuff off into swap space. And that basically enables your computer to keep working on memory-bound tasks. But the trade-off, of course, is that your hard drive is incredibly slow compared to your RAM. So if your system is trying to access stuff that's in swap, it's going to take it orders of magnitude longer. And generally speaking, what the user notices is that when you fill up your RAM and start to run off into swap, everything about your system grinds to a halt. It takes you minutes to actually get a response from your operating system when you try to click on something if you've consumed all of your memory space. So oftentimes, in some ways, a memory-bound operation is one which is going to be more noticeable to a system than a CPU-bound operation, because your CPU has clever ways of handling a lot of load on itself. It'll juggle tasks, and it'll lower the priority of some tasks. It'll slow some tasks down to keep itself responsive. Where if you eat up all of your system's memory, pretty much everything will grind to an excruciating halt. An I/O-bound program is one that has to read or write frequently to your hard drive storage. There are not a lot of cases of this now, but one area where memory-bound and I/O-bound programs might interact is if you have a truly gigantic data set. One thing that you might have to do is sort of work on chunks of that at a time, which means that what you've got to do is read like a tenth of that data into memory, work on it, then write it back. Then read the next tenth into memory, work on it, and write it back. And this means that instead of just being able to load the entire data set from storage into memory all at once, you have to keep putting bits of it into memory and then writing it back to the storage system. And that back and forth between storage and memory is a slow process. And so if you have to do this, generally speaking, it slows your analysis down because that travel time takes time. And it takes a lot of time relative to just kind of working on stuff in memory and pushing stuff between the CPU cache and memory. The fourth kind of performance bottleneck, which we will see vastly more rarely, but which on a true cluster you will see sometimes, is a network-bound performance bottleneck. And this is where your data or your program has to communicate over some kind of network a lot. So this tends to happen in web applications a lot, where your program has to ping some server somewhere to get a response to do something. And it might have to ping multiple servers. It might have to ping one which runs a calculation and another one which loads the data for the calculation. And a problem, of course, is that your network download and upload speeds are, on the whole, even slower than your hard drive read-write speed. So my internet speed at home, uh-oh. Speaking of network-bound operations, this is fun. There we go. I think we're back. So if your system has to communicate a lot, if it has to ping a remote system many, many times to do anything, then that introduces the potential for slowdowns, and it can introduce the potential for network systems usually have measures in place to make sure they don't get bombarded by requests. That's what if you see news about a DDoS attack on internet infrastructure, that basically means that some malicious actor is slamming that server with many, many trivial little requests. And in order to handle all of those requests, the system slows down a ton because it has to sit and work on each one. So a lot of network infrastructure has stuff in place to prevent you from doing that, which means that you have to introduce delays in when you talk to your remote systems. And one place where you will sometimes see this happen is if there is a delay in submitting a command to the RStudio server on one of the TCore systems through the browser client. Often that is a delay that's a network introduced delay. Like maybe your internet is slow that day. Maybe the university network is getting a lot of traffic. Maybe maybe that specific computer is getting a lot of traffic, and that'll slow your operations down. For the most part today, I'm going to focus on CPU-bound tasks because this is kind of the traditional performance bottleneck that we're going to try to get around. And these happen a lot because a lot of the statistical and modeling analysis that we want to do take a lot of power to do, and they take a lot of calculations to do. And one of the things that has been a consequence of the fact that computing power has gotten both cheaper and much more powerful over the last 30 years is the fact that we can write analyses which take a ton more power to run than we could have 20 years ago even. And as a consequence, we have to come up with cleverer and cleverer ways to get around them, but also we often are now more comfortable with writing code which is less efficient, but easier to write and work with. And this is a thing which anyone who has come from, so if you're lucky or unlucky enough to have written code in C or Fortran, C and Fortran code is really, really fast. Like it is vastly faster than anything that R can do natively or that Python can do through its interpreter. But it's not fun to write, and it's not fun to write complex analyses because you're writing at a much lower level and you're talking to the system at a lower level with fewer language abstractions that make the code you're writing look easier to read to a human. So as we get languages like R and Python and things that are easier to work with for humans, we're often having to deal with the trade-off in the absolute performance of those tasks in order to get that speed up. So one way to think about CPU performance and program performance in general is a thing that's called big O notation. And the idea here is that we want to get a sense for how does the number of calculations that your program has to do scale based on the size of input that you're giving it and the complexity of the program itself. And what we're thinking of here really is kind of the asymptotic answer. So in the limit as the number of the amount of data you're putting in or the amount of operations gets big, in that limit, which scaling factor is the dominant one? So big O notation will usually look like O of some function, O of n squared, O of the square root of n, if you're vastly lucky, O of n factorial. And what this means is that if you gave this thing an asymptotically big data set to work on, the number of operations required to complete that program are the size of the data. Say if you have an O(n) squared operation or program, that means that it will take on average, say, the size of the data squared, and that many calculations are needed to complete it. So an example of this is if you're performing a matrix multiplication in pretty much any language under a naive, straightforward implementation. This is an O(n) cubed calculation, largely because and n is the dimension of any of the matrices, or one of the dimensions. So if you're multiplying an n by m times an m by p matrix, I think that's right. I might have reversed the dimensions. But in any case, if you're doing that, what you essentially need to do are n times m times p calculations, which in the limit is roughly an n cubed thing. So what this tells us is that multiplying matrices is actually a pretty slow operation as the size of the matrix gets big. Like if you're multiplying a 2 by 2 matrix by a 2 by 2 matrix, you're fine. But if you're multiplying, say, a 1 million by a million matrix by a million by a million matrix, now this is not so fine, because now you have to do a million cubed operations, which is many, many calculations. So this gives some sense for why some things take way more time to calculate and use way more space on your computer as your input data set gets bigger. And in fact, matrix multiplication is a good example, because matrix multiplication is used a ton in pretty much everything. It's used in statistical analysis. It's used in modeling. Like if you do regression of any kind, that regression is performing matrix multiplications. And so if the data that you're giving it is truly huge, that matrix multiplication is going to take a bit, and is going to take quite a bit of space. If you're working with Markov models use matrix multiplication to solve for a lot of critical stuff in them. So if your model has a really big state space, then you could be looking at a large number of calculations to complete your model. Generally speaking, when we're thinking about performance of programs, obviously, so this graph here shows how different sorts of big O speeds look compared to each other. A really nice case, which we don't get very often, is what's called linear performance, where the performance of a program just increases linearly as the size of the data increases. And anything slower than that, we tend to think is potentially a hard problem as the data gets big. And anything faster than it, we don't really care how big our data is. Like you could have a billion entries, and if you have an algorithm which scales linearly, it doesn't make a huge difference if you have a million versus a billion pieces of data. Where if you have something that scales in n squared or polynomial time, or worse, in exponential time in 2 to the n or factorial time, you may not actually be able to reasonably complete those calculations before the universe is consumed by heat death, if you have sufficiently big data going in. And so a lot of work that we do trying to optimize the performance of algorithms is to try and avoid problems that give us things like O(n) squared or slower algorithms. In some cases, it's just unavoidable, like big matrix multiplications are just slow. So at best, these things have gotten down to like somewhere in between O(n) squared and O(n) cubed time scaling. But that's still a pretty slow thing, and we just kind of have to deal with it and try to find other ways around it. So there's a lot of computer science focuses on proving that an algorithm has one scaling or another. Like if you can prove that your algorithm has O(n) squared time scaling, you've got a very good algorithm. Or if you have n log n performance, that's a really good algorithm for something. So it's just a way of thinking, like if I'm doing an analysis, how fast or slow do I think it's going to be? So often the way that I'll frame this, even if you don't necessarily know what's going on under the hood, is one way to think about it is does my thing have to do any matrix multiplications? And if it does, then I might have something that could get slow and fat in memory terms as I put in a bigger and bigger data set, because the data set is fundamentally a big matrix. So that's kind of a way to think about, do I expect my program to slow down as my data gets bigger? Any questions at this point?
So
Or comments?
maybe one question here. Saying the graph, like lowercase n, is the size of the data?
Yes, essentially. It's
then,
the size of the data, or the size of the input for a program.
Yeah, but then the capital N, how do we interpret capital N here? The uppercase N, the y-axis? What is?
Oh, I see. Oh, I just treat that as O of f of n. So that's an arbitrary variable for the time on this scaling.
So basically, like measuring some performance.
Yeah. So if I put in a size 50 input in a linear scaling thing, then it would give me a 50 output. The actual number of the output is not important in this case. It's sort of the shape of the curve is what matters more than anything. So how fast does it go up as my lowercase n increases?
Okay.
Well, actually, any other questions on things that I've covered so far? All right. So then, if we find ourselves in a case where the performance of our program is not so good, one thing that we can try to do to kind of cheat is to parallelize our program, or to get around that. Because even if you have, suppose you have to do a lot of matrix multiplications, and these things are n cubed, if you could split that up into 10 smaller matrix multiplications, even though each of those is still n cubed, in the real world, you do still actually get a meaningful speed up by having each of those be 1/10 n cubed. So one thing to keep in mind about big O notation is that this is in kind of the worst case scenario. But in the real world, when you're writing a program, there are other factors that can kind of improve the actual amount of time that your thing takes to run. So all parallel programming is basically is looking at your problem and splitting it up in a way so that you can give a chunk of it to any given processor. So you split your problem or your data into independent chunks, and then work on each of those, and then put the result back together at the end. So why would we do this? Well, to improve performance, to kind of flip my answers here for one, because again, if I'm multiplying a matrix that's 1,000,000 entries long, then if I divide this into 10 things, then each of those is only 100,000 entries long. And that is meaningfully faster to work on than a thing of size 1,000,000. And if I can do all of those 100,000 sized matrices simultaneously and then stuff them back together, well, that should be faster than working on the whole 1,000,000 by 1,000,000 matrix kind of sequentially. But the other reason is that pretty much every modern computer processor, and this even goes for the things in your phones, has more than one core. So at some point, processor manufacturers figured out that they couldn't really make a single processor faster without making it use so much heat that it functioned as a space heater, and drawing so much power that it increases your electricity bill by a noticeable amount. So what they started to do instead to improve the performance of computers was just to put many processors together. So that's why in my original diagram, in the old style, you had one processor that executes your instructions one by one. So that's fine. But now every processor is actually made up of between 2 and however many cores a CPU manufacturer can cram into that thing. So your average laptop nowadays has about 4 cores. So does your average phone. Phones tend to have between 4 and 8 cores, and your average desktop will tend to have about 8 cores. So this means that theoretically, a processor that has 4 cores should be able to do 4 things simultaneously, which means that if you had one task that you could break up into 4 tasks, it should, in the ideal case, take a quarter as long to run that one task. Of course, the difficulty here is that it is harder to write parallelized code because this depends on whether the problem that you have can actually be broken up into independent chunks. And not all programming problems can. There are some that where the next result depends on the previous one so much that you can't split those apart. So you only get this performance benefit of having multiple cores if you can divide your problem up in a way to send it to those multiple cores. And B, you don't necessarily get the maximum speed up from parallelized code that you might think. So generally speaking, even if I can divide my code nicely into 4 chunks, I'm not going to get it to run in a quarter the time as the original thing, because there's a little bit of extra time spent breaking the code up, working on it, and then putting it back together. So that extra overhead in some cases can be so big that it actually overwhelms the benefit of parallelization to begin with. So while in many, many cases, and especially for big slow analysis, parallelization will almost always speed you up, sometimes it won't. And part of what I'll talk about in the second half really is sort of ways to try to figure out when parallelization might give you an actual speed up versus when it might not. So there are, technically speaking, multiple ways to parallelize your code at different levels. Okay, the lowest level parallelization tends to be thread-based or instruction-level parallelization, where little groups of instructions are distributed among cores. So maybe you send a chain of additions to one core and a chain of multiplications to another core and so on. And this tends to happen within, at a lower level within a program. So thread-based parallelism tends to be something that will be implemented in lower level languages like C or Fortran. Process-based parallelism is what we'll tend to look at more. So this is where the programming language and the operating system create worker processes, which are basically little programs where you give them stuff to run, and each of those sits there and waits for instructions and then eventually puts that all back together. So instead of distributing out little groups of instructions, what these are going to take are discrete chunks of your program, run them, and put them back together. And this tends to be the dominant mode for higher level languages like R and Python, where they don't have access to lower level constructs to distribute out instructions or threads. Under the hood, they might actually be doing that, but to the programmer, they're dividing your code into a bunch of processes, or they're creating processes and then sending chunks of your program into each process to finish working. Kind of a version of process-based parallelism is batch processing, where you submit multiple copies of the same job at the same time. So this is where you'd submit 15 copies of your R script, and the computer runs them simultaneously and then spits out the results, which is basically process-based parallelism at a bigger scale. So usually when I'm talking about process-based parallelism, I'm thinking about something that's happening within the code you're writing itself, as opposed to when you go to run the whole thing and you throw out 15 copies of it and let those come back to you. In R, as I mentioned, parallelization will tend to happen in a process-based or batch mode. And there are a number of different packages that enable this. In the core R language, there's the parallel package, which creates what's called a cluster, basically a cluster of workers, and then sends jobs to those workers and then reassembles the output of those jobs. What this means is that R's parallel package can work in a couple of ways. It can work on multiple cores on the same system. It can theoretically work across multiple systems if you define a cluster to include multiple systems. This I haven't played around with much, but it does exist as a feature. And the primary mode of working with the parallel package is through a parallelized version of the apply functions in R. So in R, apply functions tend to be used to perform a task multiple times on a vector. So it's the equivalent of a for loop, but using what's called a vectorized function. And I'll demonstrate that later because there's an interesting kind of quirk in R, which means that vectorized functions like apply functions are really fast. So fast, in fact, that there are cases where they actually work as fast or faster than parallelized versions of similar things. There is also the for each and do parallel packages, which essentially enable you to write parallelized for loops. So instead of using the apply function to do a task repeatedly, you can write a parallelized for loop to do the same thing, but with a syntax that might be more convenient or explicit for a given piece of code. So if you're working with R packages to do parallelization, you'll usually either use the parallel package or the combination of the for each and do parallel package. So if you use for each and do parallel, you have to install both. In all cases, you'll have to load them into your current library, and I'll demonstrate that in a sec. These are a couple of sites that I've found that I think offer good introductions to parallel computing in R. They walk you through using both of the packages and show you examples and output and things like that. So what I'd like to do at this point is move into a little bit of a demo of parallel programming in R specifically. So let me swap over to my second RStudio window. So I'm running these things on T-Cores 3 because some folks are running tasks on T-Cores 1, and I don't want to get in the way of those because some of my examples can get large. So if you look at my, my RStudio editor here, what I have open is a script called paralleltest.r. And what this is doing is demonstrating the usage of the parallel package. So before I start with this, actually, I'm going to take a quick break because I need to use the restroom, and I will give you all folks a chance to get up, grab a drink, or use the restroom, as the case may be. So give me like 2 minutes, and we will reconvene. Thanks. All right, we're back, and let us proceed with the little parallel demo here. So, so here there's a little bit using the parallel package that you need to do to set things up. So here I've loaded in the parallel library, which fortunately is pre-installed in our distributions. And then there are a few things you can do. So one thing I've done here is I've used the detect cores function to figure out how many cores my system has available. Yes? Or was there a question, or no? I guess not. So here I'm going to comment a bunch of stuff out right now because I don't at the moment want to run a bunch of this other stuff. So if you have worked with RStudio before, there's a few ways to run code. You can select lines and run them one by one. You can run regions. I prefer to just source files because I don't like line by line running. I think it's a dangerous paradigm. So I'm just going to source this file. And what I can see is that my system tells me I have 255 cores available. This is actually a little bit strange because this computer has 128 cores, and so this should probably show up as 256. But it's also possible that the parallel package can't actually, like that it has an upper limit of the number of cores it can detect because it wasn't written to understand that systems could have this many cores. So also, one thing to note is that on pretty much every modern system, if you ask it what its core count is, you're going to get a number which is double the number of cores that it actually has. And this is because modern processors implement a thing which makes them look as though they are twice the processor that they are for specific operations. It's called Intel calls it hyperthreading. I think I've also seen it as simultaneous multi-threading. I think I might be getting that wrong. It's the acronym is SMT, but the idea is that modern processors are powerful enough that if you give them two sets of instructions at once, they can swap between them fast enough to make it look like they're working on them both simultaneously. So it takes advantage of the fact that operations that you give a processor don't necessarily use all of that core. So this is why most modern processors will look like they have twice as many cores as they actually do. And the difficult thing, of course, is that a processor that's split like that is not actually as powerful as two processors or two cores. Like a core with an Intel core with hyperthreading is not actually two proper cores. It'll only behave like that if you give it code that can efficiently take advantage of the fact that it can kind of swap between two sets of instructions pretty quick. So generally speaking, when you look at the number of cores available on a system, unless you know that it does not have SMT enabled, you should assume that it has about half the cores that the system actually tells you and kind of work with it accordingly. This is also an area where I would recommend testing things because if you're working on your own system and you're able to completely load it, like nobody will yell at you if you use all the cores on your system, it's often worth testing your code to see whether it actually speeds up if you start asking for cores beyond its maximum physical core count. So for all intents and purposes, what I probably want to do is something like print the number of cores divided by 2. Well, round that. To tell me how many physical cores my system has access to. So then the next thing I'm going to want to do is use the parallel package to make a cluster, or what it calls a cluster, which is basically a group of workers that it's going to send my parallel code to. So there's a few ways to do this. And I'm going to use the help viewer here. So the most general way in the R parallel package is a function called make cluster. And what this will do is create a cluster of workers using multiple possible methods. There's more or less two types of clusters that R can create. One is called a PSOC cluster, and the other is a fork cluster. The PSOC cluster is its default. And what this does is it creates a cluster of workers using your system's networking interface, which is kind of a strange way to do that. But what that allows is to make clusters which span multiple systems based on their network address and things. One interesting consequence of this, which I need to spend some more time testing out because some of our researchers who've been using these systems have bumped into it, is that by default, R has an upper limit on the number of socket connections it can open, which also means that it can only create so many, it can only make a cluster of like size 100 before it throws an error using the PSOC cluster method, which puts a bit of an upper bound on the number of cores that you can use if you're using a PSOC cluster on a single system. Fork clusters on Unix systems, so Linux and Mac, but not Windows, basically work more straightforwardly. They just spawn processes that R sends code to. So if you make a fork cluster, what you're going to see in the terminal is in the system monitor is a bunch of R processes show up. And each of those R processes is running an instance of the code that I send to it. So in my case, what I'm going to default to is making fork clusters because on a single system, I think that tends to be the more performant way of doing this. So here, I'm going to make a fork cluster, and when you make one of these things, you tell it the number of nodes to generate the cluster on. So in this case, I'm going to make a 10-node cluster, which means I'm going to request 10 of the system cores to make this cluster. And then down here, I'll destroy the cluster. And this isn't going to produce any output, but one thing to note is that it does take a little bit of time to create a cluster. And that amount of time factors into the efficiency of your analysis. So I'm going to move on. What we're going to do here is create a fake little example to kind of see how parallelization works. So what I'm going to do is make a matrix that has 1,000 columns of 10,000 length data. And this data is just going to be generated by random normal distribution. So each row is going to be 10,000 random normal variables centered at 0 with a variance of 1. Then I'm going to run a little bit of code using the built-in rapply function to take the average of every column. And I'm not, this is returned as a variable, but the result isn't actually very useful for anything. And then I'm going to ask the system how long that took. I'm going to do the same thing using the parallel apply function here. So the apply function syntax takes the data that you're going to operate over, the axis to apply a function to, and then the function you want to do that to. So what this is going to do is axis 2 means every column, axis 1 means every row. So what I'm doing here is, since this data is a matrix, I want to take the average of every column. So I've given it axis 2, and the function is mean. The parallel apply function works almost the same way, except the first argument is the cluster that you created for the parallel package. So this is the cluster of workers. I'm going to give it that object, and then the data to work on, the axis to apply to, and the average. So this apply function is the equivalent of writing a for loop that's like for I in 1 to m mean test I. So take the mean of the column. It's a more compact syntax, but it is also faster because, well, I'll talk about this in a moment because this gives some interesting results when it runs. And this stuff, this system.time, this is a function which is super helpful if you're doing any kind of benchmarking on your code. So what system.time does is it basically tells you how long whatever you did within that function works. And you'll see a more elaborate example of this. You can actually enclose a ton of code in a system.time call, which is quite helpful. So we'll source this thing. It's going to take a bit, and then it runs. So here's what it told me. The sequential mean, so calculating this thing as though it were a for loop, took 0.1 seconds of user time, 0.048 seconds of system time, and had a total elapsed time of 0.15 seconds. These outputs are basically, so the elapsed time is the easiest one. This is the amount of time basically that I experience waiting to see an answer come out of this time. The user time, this is the amount of processor time that was used calculating stuff. And then the system time is the amount of time the operating system spent working on this. So the two values here that tend to be most important are the user time and the elapsed time. So we can see that in the parallel version, slightly less CPU time was used, but at the end of the day, basically the same amount of time elapsed from the part of the user. And this is one of those cases where parallel code is not necessarily faster. The reason is twofold. So the apply function in R, like I said, is really fast already because this thing is coded in either C or Fortran. And basically, so within the apply function itself at a lower level, there is a for loop, but that for loop is a C or Fortran for loop, which is vastly faster than an R for loop. Also, the rmean function is calling a C or Fortran function, which works pretty fast. So this combination of apply and mean is able to execute quite quickly over this data set. One question might be, what happens as our data gets bigger or as we have to iterate over more things? So right now we have a 10,000 by 1,000 matrix. Suppose we have to iterate over 10,000 columns instead of length 10,000. So I'll source this. And now for one, it takes longer to initialize because I'm making a large bit of data. Here's our sequential mean, and here's our parallel mean. So here we see that the sequential mean took only very slightly more time to me until something came out, but it did take meaningfully longer CPU time. So here's where we start to see the parallel execution improving its speed. And if I scale this up by another factor of 10 and make this a 10,000 by 100,000 matrix, well, again, this first step, this data creation step, is actually a pretty slow step because I have to generate a ton of random numbers. And this is something that if you're thinking in terms of, well, where's the speed up for parallelization, you might think, well, why not parallelize this thing? Because we can. We're drawing hundreds of thousands of independent random numbers. So couldn't we just blast that out to all of our cores and get it back faster? And indeed we can. I'm going to demonstrate a case of that after this that uses a different parallel infrastructure. But for one, this is showcasing potential slowness in sequential operations as your problem gets bigger. Like a 10,000 by 100,000 matrix is a lot of random numbers to generate, and each random number generation is a few calculations. And this can be consequential in things like stochastic models, or for those of us who've worked with smoking history generators, these are by and large stochastic models that have to generate multiple trajectories using random number generation. And so if we have ways to speed that up, that can take us from waiting a day to waiting a few hours for our thing to finish. And that's quite nice if we can get that. So here we have another interesting case. Now at this scale, I've actually taken longer from my observer's perspective to do the parallel run than it took me to do the sequential run. However, it did still take me less CPU time by quite a bit. And some of where this is happening is the fact that I can send that data out and it doesn't take very long to work on. But what's happening afterwards is that because I'm sending out 10 chunks of data, those 10 chunks have to get put back together at the end into my into my output matrix. It's not like each node remembers that it needs to slot things back in. So at the end of all of this, there is still kind of an assembly function that puts my data back together that takes a certain amount of time. So we might be apt to wonder, well, I ran this on 10 cores. Does it matter if I throw more cores at the problem? And fortunately, I wrote a script to do just that. So I'm going to do the same thing, except I'm going to make a 1 million by 20 matrix. So each row has 1 million entries, and there are 20 columns. And we're going to request this same operation on it, except I'm going to make clusters of size 1 to size 20. So I'm going to go from 1 core to 20 cores, and we'll see how that does. So I'm going to source this code. There's nothing terribly exciting happening here from a programming perspective. I generate my input data. I time my sequential run because I want to know how long it took me to calculate the means iteratively. And then I write my for loop. And in the for loop note, I'm generating a cluster, executing stuff on the cluster, and then destroying the cluster so that it doesn't stay open waiting for instructions. And then at the end, I ask for how much time did the sequential run take? Not very much. And then I've asked for a graph of the, so this elapsed time, so the observer's time, as a function of the number of cores. And we can see that broadly, as I increase my number of cores, my elapsed time goes down at a decent rate, but not as much as we might have expected. Again, because there's overhead in this operation in putting the data back together at the end. So I could make a more dramatic case here if I have, say, 200 columns, and I want, I'm going to go up to 40 cores here. So I'm going to change the number of, oh, that's going to break. Change the number of cores and change the number of columns, and we'll see what this looks like. We'll also find out from this how much longer the sequential run takes, because that'll give us some information about the comparative performance. Because generally speaking, if your sequential run is taking you less time than your parallel run, there's not really a reason to be doing the parallelization. So this is why I think it's important to know how your code is running. Like, the reason I suspect that this is happening is because I'm using the apply function, which is fast in R. And so that tells me if I'm using the apply function to run my thing, maybe I will not need to parallelize. But if my problem is big enough, like in this next case, I am making something decently big, and we can see that in the amount of time that it's taking to run, then maybe it becomes beneficial to actually parallelize the problem. Some of these test cases will also be a little bit weird from a performance scaling perspective, because in order to make them execute within the time span of this workshop, I had to make them kind of small applications, because if I made them too big, then well, we'd be waiting days for them to actually finish. And to a certain extent, that's the scale at which parallelization starts to really make sense. If you know that your thing works on a data set that's so big that it takes you 5 days to finish an analysis, that should be a tip-off that you have something big enough that parallelization will make sense. As opposed to, if it's something that finishes in seconds or less than a second, there's probably no reason to bear the overhead and additional programming complexity of parallelizing your code. That being said, there are other performance optimizations you can do in the meantime, like the fact that we know that the apply function is fast, but a for loop is slow in R. So any time where you can replace a for loop with an apply function, you're going to get a pretty big speed up in your code. And things like that. Generally speaking, R likes using vectorized functions instead of loops. So if there's any time that you can replace a loop with a vectorized function, that will make your code faster. That being said, it will also make your code less explicit. So if you don't need that performance benefit, then I would tend to prefer writing for loops than using applies as a stylistic thing. Granted, R code frequently uses for loops, so we're often accustomed to seeing them, but that's not always the case. And I think having the explicitness of a for loop can help, because this tells me exactly which instructions are being executed at every step. Note also that the parallel runs here are not the fastest things in the world. And I'll use this as an opportunity to kind of take a look at what the system's doing. So I'm going to use the htop command, which is a more elaborate system monitor. This thing will show me what the cores are doing across the system. So one thing that we can see here is that right now the cores are not actually loaded very much from anything I'm sending the thing. And this is a tip-off that the application that hello, let's move this around a little bit, that the thing I'm running is not using an enormous amount of computational power, but what it is using at this point is either input-output or well, likely input-output, because in order to run this thing, it has to disassemble and reassemble its job or its data, and the data is decently big, and so that process takes a bit of time. In this case, it's actually taking a weirdly long amount of time, and for reasons that are not immediately obvious to me. So this is a good case of trying to investigate what is happening here. So I can, oops, actually. So one thing that's happened is I have a lot of stalled R sessions running, which likely means that the system was not able to kill and clean up some of the worker sessions that it produced. I'm not 100% sure why it decided that would be a problem, but this sort of thing can cause parallel operations to stall. So I don't want that. So we're going to kill our thing here. And just to be extra sure, I'm actually going to restart the R session so that it destroys the cluster sessions that it produced. And that should hopefully solve that problem. So now I've removed all of those. Apparently, the lesson here is that I should be careful about the size of things that I'm testing. Like one thing that the rparallel package does not like doing, which I'm forcing it to do here that's really awkward, is it does not like sequentially creating and destroying clusters. It prefers that what you do is create a cluster, work on it, and then destroy it at the end of everything. So this sort of test is kind of not a healthy thing to be doing on using R's parallel package. Other languages handle this sort of thing more gracefully. R is a little bit not so great about that. I think I might have had another example in which I can maybe get at some of this better. Well, actually, I can do this crudely using this parallel test. So here, remember, I made a large matrix and then I worked on it with my 10 core cluster. And we found that when I made a 20 core cluster on a smaller thing, I still wasn't hitting parity with my sequential run thing. So we can build bigger clusters. So if I give it a 64 core cluster, this is half of the physical cores on the system. We can see how it handles that. So it'll take a while to initialize, and then we'll get running. And while it's doing that, one of the things here too is that the more cores you send your job to, the more overhead you incur in terms of disassembling and reassembling the data that your code is working on. So that can be why, in this case, we tend to see that some of the kernel time and the observation time of how long the thing took to finish can get kind of big, because all those cores have to talk to each other, and then they have to put your stuff back together and stick it back in memory. Note also that we can see, for example, how big our data is here. Oh, I should not have clicked that. Hang on, I'm gonna kill this. And I don't usually work in interactive environments, so I get a little bit loose with my cursor control. So we'll start that again. But we can see that this data set takes up 1.5 gigabytes, which is decently big. And what that means is that if I needed to work on it a few times, I might need to make copies of it, which means that I'd need to make 1.5 gigabyte copies of the data set. And if my system didn't have a lot of RAM, that could be a problem. It also makes it easier to see how quickly you can make a data set that's really, really big. And I think for folks that have been working on, like, I have observed that Jiyun works on data sets which are truly massive and that take things approaching the order of terabytes to store. And if they're doing that, that means that they take a lot of memory on the system to work on. And when R works on data, it tries to load that data all into system memory. So this can be why, if you're working in R on your laptop, and especially for those of you with Macs, if you're trying to work on a decently big data set in R on a MacBook, sometimes it'll just crash, or it'll stop, or it'll slow down, because Macs don't have a lot of memory available to them. And so if you're working on, say, an 8 gigabyte MacBook, the biggest data set you can store in memory is 8 gigs, but it's worse than that because everything else your computer is running takes some memory. So you use memory when your operating system is running. R itself uses a certain amount of memory, and then every operation you perform on your data set consumes a little bit of memory too. So in practice, you actually can only store something which is a fraction of that 8 gigabytes before your system sort of slows down and breaks. I'm suspicious also that my system is forcing me to not create this many parallel jobs, which is interesting. So we're gonna kill that again. And in the interest of moving on, I'm gonna stop this part, which also means that I'm going to spend some time figuring out why it doesn't like creating jobs of this size. Generally speaking, if you're interacting with one of these systems, please do not try to use up more than, say, 10 cores unless your job really requires it. Like I'm asking for gigantic clusters, and that's R is not intrinsically designed to handle that. The thing I do want to demonstrate is the for each do parallel structure of running code. So I mentioned that this was an alternate way to parallelize code on a, let me just make sure that I killed all of the extra stuff, and it looks like I did. This is an alternate way of parallelizing your code that uses for loop syntax. And the reason you might do that is that there are some times when trying to cram your code into an apply function shaped hole can be really awkward. So what I'm kind of doing here secretly is I've written some code that is essentially doing what a big stochastic simulation would do. So here, first of all, I'm gonna load my two packages, and I'm going to register my cores with the do parallel package. So this is analogous to in the parallel test where I make a cluster. And I'm only going to register 4 cores for now because I'm pretty sure that this is a demo that I can do without breaking anything. And then in the sequential version, what I'm going to do is time this for loop here, where for 10,000 steps, I'm going to draw 10,000 normal random variables, 10,000 uniform random variables, and 10,000 exponential random variables. So each time step, I'm drawing 30,000 random variables of different kinds. So if you run stochastic models, every time step you have to draw a bunch of random numbers. It's not always this many, but when you run stochastic models, you have to run your model many times. So I might run it for 10,000 time steps 10,000 times in order to calculate a stable average trajectory from the model. So that might then look like 10,000 random numbers drawn 10,000 times. Now, when I want to do a parallel version for this, I'm going to use the for each function, essentially. And the for each function is defined very much like a for loop with a few little differences. So notice that in a for loop, when you're iterating in R, you say I in some range. So your iterator over some range, but you use in to tell it that this is what you're iterating over. In for each, you use equals, but otherwise it's basically the same. Then this bit is followed by this little decorated statement. In this case, what's this called? %, do par, %. And what this is going to tell it is execute this using the parallelized version of the for loop. So all this is saying is the system is going to look at this for loop and divide the thing into 4 chunks, because that's how many cores I registered. And then it's going to send a quarter of the runs to each core and then put it back together at the end. And then again, I'm going to time the execution. So we're going to source this and hope that nothing breaks. I was testing this on T-Cores 1, and it's entirely possible that there could be some differences between the systems that cause this to break on one or another. So here's our sequential run. That means that there are some zombie connections left open here. We'll fix those eventually. But here we can see a more convincing demonstration of parallel execution. So in the sequential run, where I had to draw 30,000 random numbers 10,000 times, it takes me about 9 seconds, and about the same from the CPU's perspective. But when I run this in parallel, it only takes me 4 seconds from my perspective. But the bigger speed up is at the CPU time. This almost takes a quarter of the CPU time. And again, the reason for the difference in CPU time versus observer time is that the CPUs themselves didn't have to deal with all this extra overhead of taking stuff apart and putting it back together, where me sitting here at my desk waiting for this, I did. So by using 4 cores, I get a speed up factor of about a half, about 2, where at the CPU level, it's getting a speed up of nearly 4 times. So this example hopefully is more convincing in demonstrating that when we parallelize stuff, sometimes we do actually get pretty big speed ups. I'm going to try 8 cores, and we're going to see if these zombie connections cause me a problem here. They might. So here's our sequential run, takes about 8-9 seconds. Here's our parallel run. Oh, that's fun. So that took a lot more CPU time, but a lot less elapsed time. So again, there are some weird trade-offs that happen. And also, this means that when you're measuring the time of your execution, sometimes you have to use different metrics to figure out if you're actually getting a speed up, because the CPU time can be influenced by a lot of stuff, where sometimes you want to use the elapsed time, sometimes you want to use the user time. But again, we're tending to get a decent speed up by distributing our 10,000 iterations of 30,000 random number draws, as opposed to just running them in sequence. And broadly speaking, the speed up will tend to increase as we force the thing to do more calculations. So if I did this for 50,000 iterations, we should see more of a speed up still. I can make this code available also if you want to kind of play around with it and test out when it works well, when it works poorly, when it just straight up breaks the system, because sometimes it'll do that. And this is, again, one of the complexities of working with parallel code, that it's much less straightforward to just execute, because you tend to have to play around with debugging it more to figure out, I thought this should work, but apparently it just crashed, or it soft crashed, or it just hung at some point and didn't do anything else. So when you're working with parallel code, there's extra stages in making sure your thing goes, for one, but also making sure that it runs in a way that gives you the speed up that you want. So since we're running up on the end of the session, I'm going to swap back to just a couple of ending slides to bring this back a little bit to, so for one, when do we want to parallelize based on all of this? Well, generally speaking, if you have a computationally intensive task which you have to execute a lot, then you might think that parallelism is a good way to address it. And in general, it usually is. Also, if your problem can be subdivided into discrete independent components, like if you're doing spatial stuff and you need to do the same calculation for every, I don't know, for every hectare grid in the state of Michigan, then that's a great parallel operation because each operation on each hectare doesn't care about any other hectare. Also, if your code uses a lot of for loops, those for loops are awfully slow. And you generally want to try and avoid that. And so you can get a speed up if you parallelize your for loop as opposed to running it in sequence. Of course, we've seen some of the potential issues at the scales we're looking at for smaller problems where the calculation time versus data transfer and setup time can make your trade-off rather awkward. So for all of the problems I showed where they tend to take less than an hour to execute, parallelization is not necessarily the best approach. Also, you have to think a lot about memory usage when you're parallelizing because if I have a system which has 8 cores and 16 gigabytes of memory, that means that it has 2 gigabytes of memory for every core. So if for some reason I try to give it a task which takes 3 gigabytes for every parallel instance, we're going to run into trouble because the system's going to eat up all of its memory, start using its swap, and grind to a halt. So when you're determining whether parallelization is a good thing for your program and how you're going to implement it, you generally want to know how your code scales and how the speed and memory usage of your code scales as you distribute it. So is it the case that when you break your code up into 4 parallel processes, it uses a quarter of the memory of a big sequential run, or does it use a quarter plus change? Also, as you add more cores to your thing, does it in fact get a meaningful speed up with each core added, or is there a point where it starts to stop benefiting from additional cores? In terms of tobacco research, practically, a lot of the cases that I tend to think of as good cases for parallelization are things like Bayesian statistics and bootstrapping. Anytime you have to draw a random number hundreds of thousands of times, that's probably a good place to parallelize because you can tell each core draw a random number or draw 10 random numbers or draw 100 random numbers and then just spit them all back later. Simulation modeling, as I've alluded to, kind of combines this because you have to do a lot of random number generation in simulation modeling. You have a bunch of other calculations to do to update your system, to update who is a current smoker, who's a former smoker, and so on. And you have to run that system thousands of times to stabilize your average. And so each simulation doesn't care what each other simulation is doing, and you can either batch them or run them in parallel processes. Large data processing also is kind of an obvious one. So if you have a gigantic table, you probably don't want to, and this is not even statistical analysis so much as if you're cleaning the data or reformatting it, you don't necessarily want to have to, I don't know, capitalize a billion people's names straight in sequence. You could capitalize a million at a time split across however many cores, and that can get you a speed up in your data processing itself. In addition to a speed up in statistics, although generally speaking, statistical functions are pre-coded as black box functions, so the degree and method to which they're parallelized depends on whoever coded the thing. So it's often worth digging into the documentation for those packages to see if they can actually take advantage of parallelized infrastructure. So with that, we're at 3 o'clock, but I'm happy to try and answer some last remaining questions if anybody has them. And of course, if there are other topics, that people are interested in or seeing more depth in, I would be happy to set up another workshop down the line to try and dig into those more. When you get into computing at this scale, there's a lot going on, and so it's hard to cover that in the span of a single workshop. But thank you, and I'll take some questions.
Thank you so much, Michael. Again, this was a great workshop, and we really appreciate. Yeah, so speaking of like sharing this video and this workshop material, Katie, do you know how would you be able to share it?
Yeah, so once the workshop ends, the recording will process through Zoom, and then I can just share a link to the recording. And then I think Michael mentioned he'd be able to share his code, and so I would just share that around as well. I could look into creating an Mbox folder with all these, but I think just sending the link to the recording is probably the easiest, and it allows access to everyone.
Yeah, and I feel like we also have that video, recorded video somewhere, right? And then
from the first workshop?
Yeah.
Yep, so I could include that as well.
So, and I feel like maybe if we have some kind of a central place that the people can go, do you think that would be easier to manage all these files?
Sure, I can work on putting that together.
Yeah, that would be great. Okay, thank you. Well, so everyone, do you guys have any question?
Hi, this is Luz. I'm just
Hi.
a very quick question. You mentioned that running parallelizing in Mac will become slower, or it takes longer time, or it crashes more often. Do you recommend just to do it in like Windows or other one?
Well, it depends a lot on the system it depends a lot on the hardware configuration of the system that you have. If you're running parallelized code remotely, it doesn't matter what your system is. So when I'm running code on one of the TCore systems, it doesn't matter if I'm running it from a Mac or from a Windows machine or from a Linux computer. Where it does matter is if I'm running the code on my computer itself. And the reason I mentioned Macs is that by default, Mac laptops don't tend to have a lot of RAM, where comparable Windows machines will usually have more memory. So it's just, it really comes down to how much memory does your computer have versus how many cores does it have, and that will tell you something about whether you can whether you'll be able to parallelize on your own home system. Also, for personal laptops and things, they are often not quite big enough in some sense to make parallelization worth it. So that's something to consider too. Let's see.
Luz,
Yes.
you have an account in TCore server, right?
Yes.
Try then, you can use the TCore server to run your program.
To run my program. And just one question before. So at the beginning, you showed different like internet addresses, and one was like TCourse project 1, 2, and 3. Does it depend which one we use? Can we use anyone, and we just see how many people are using it now, and then move to another one?
Yeah, that's certainly possible. You can use either TCourse 1 or TCourse 3. I've made accounts for you all on TCourse 1. I will make accounts for you all on TCourse 3 moving forward. TCourse 2 is sort of by TCourse 2 is only accessible by permission of Raphael and folks, I believe.
It's like project. Okay, good to know. Thank you.
And for Eugene, I just tried your login on TCourse 1. That one definitely works. If you're trying to log into TCourse 3, I haven't made an account for you on that one yet, so that could be the cause of this. Let me just paste your... There, Eugene, should be your username and password for TCourse 1. And let me know by email if that continues to not work. And I should have accounts for everyone on TCourse 3 by the next couple of days.
Just one last one. So the example, the code that you use as an example, can we use it the way it is, or we need the database, or in the server?
This code should be entirely self-enclosed, so it doesn't read any data in, it generates it at runtime. So as long as you have the packages installed that it uses, you should just be able to run any of the scripts that I've written for this demo.
Okay, perfect. Thank you.
Okay.
All right.
Yeah, I think, yeah, that's all for today. Thank you. Thanks a lot, Michael.
Thanks everyone for attending, and let me know via the survey what you thought and if there are any other topics that you'd be interested in hearing more about.
Thank you.
Great. Thank you. Bye-bye.
Great.